Carlo Bottiglieri, and she's Elena Vilchik. We are recording this because yesterday we could not give our presentations at the MunichJS, so I hope you are gonna watch this instead and enjoy it. So let Elena begin.
Okay, hello everyone. Thanks for watching our video. And we're gonna speak today about SonarJS. This is a static code analyzer for JavaScript language, which we are developing at SonarSource with Carlo. First, I should start with difficult stuff about creating code analyzer for JavaScript. And I will not start with the details of creating the analyzer itself, but I will start more about JavaScript culture. The problem is that I should confess to you that we are mostly Java developers. And of course, it's keeping us from quite some distance from hardcore JavaScript developers. Because of course there are some idioms in that world, there are some expectations from JavaScript developer on how code performs, on some specific code structures, and every time we see something like that, we get really surprised about it. And then we find one more stuff like that, and another one, and it's a never-ending story. And the fact we never ending to learn the language so that we know all the nuances of it on how this language works, particularly for the developer. Another thing about JavaScript words is its diversity. There are a lot of frameworks which are used by developers. These frameworks appear and disappear, and many of them create their own extensions of language, which makes our job even more hard. And there is another thing is language versions, language features. Some features were suggested but not even included in specification, but thanks to transpilation you can already use it right away. And the last difficulty I wanted to discuss with you is the expectations from the code analyzer itself from the developer. Some people expect the developer provides you style rules. Other developers is more interested in bug finding rules. Other one is interested in metrics and complexity or something like that. So indeed there are many analyzers which are focusing on providing style. Indeed, that's really important to have team to have team following the same rules on naming conventions, for example, stuff like that. But in our team, we are trying to focus more and more, not on that, but we're trying to focus more on finding problems in your code, so that we will prevent you from doing some mistakes, prevent you from doing wrong steps, find some pieces of code which are not yet a problem but might become in the future. And in spite of all that problems, that's still worth it. So let's see in a real project which issues we're able to find. So we took as an example the project Prettier. This is not a big JavaScript project which is used to format the code. You probably heard of it. And here are some issues which are able to find it. On line 105, we didn't enable yet the highlighting of issues so that you could take your time to try to find it yourself. On line 105, we have an issue And if I will launch analysis, we can see it. So this is about identical sub-expressions of AND operator. So obviously, the intention of developer was to check two things, one then another one, but he or she copy pasted and forget to replace some property or something like that. Another issue is about function call. We have a function which is called with two arguments, while it is declared with one. Arguments key variable is not used, so there is no way that options argument is somehow used. So also, I don't know the story, but probably it was used someday, but now there is no point of that. It's just confusing. If we will see more comments, more interesting stuff. Here we have an issue about the flow of the code. So in this case, we have this condition of ternary operator, which is always true. And we have it because if you look for the code on this line, you have is block checked in that condition, and if this one is true, then we always leave in the function. We never reach that last line. So that means that is block is always false at that line, and ternary condition is always true. So that empty literal, which is provided as else ternary value, it's never used. And let's see now how all of that works from inside of the analyzer. Carlo will continue that.
So, how does it work? The idea is that the analyzer works a bit like a compiler. A compiler has multiple layers, multiple steps that it performs in order to model the code and get to let's say, final executable generation and optimization. So it has lexical analysis, syntactic analysis, semantic analysis, and on top of that it starts generating the results. For code analyzer, it's similar. The three first steps are common, and the two last steps change. So you get the first three, and then on top of that you can build data flow analysis, and then on top of that the last layer, the layer that uses everything else, is your rules. And I'm gonna go through all of these layers. So first layer is, let's say, really the most simple one. It's about lexical analysis. Lexical analysis is, let's split the overall text that we have into meaningful tokens. We don't try yet to interpret them beyond simple identification of basic concepts like what are the keywords, what are literals, what are punctuators, parentheses, etc., etc., and which are the identifiers. At this level, there is not really a lot that you can find from the point of view of an analyzer, but you still can write some rules that exploit this level of understanding of the code. And it's for instance, here I have an example. Here the analyzer is finding that you have prefixed your number with 0. So it's 052. And we're able to point out that probably this is not what you meant, because 052 means that it's an octal value, and the actual value, the decimal value that is going to be calculated is 42. So probably you didn't want to add 0, or maybe you wanted to write 42. I would say more likely you didn't want to add the 0, but we don't know, we just pointed out. And another interesting thing that you can find at the lexical level, really at the token analysis level, is that this token here equals plus. Well, probably is not what you meant, again, because just try to think what the code will do in this case. Is it what you really wanted it to do? So it's just assigning plus JS community.length to dev number, or what you meant was more like this, so that you were adding the number of JS community to the dev number. So this is what you can find at the lexical level. Next, you have the layer that most of the people associate to analyzers and to understanding the code, which is the syntactic level. And the syntactic level's goal is to build what is known as the abstract syntax tree. The abstract syntax tree represents the code in its, let's say, static structure. And it does it by starting from the lexical level and understanding that function keyword that you had was in fact the beginning of a function, and the function is decomposed into a function name, into parameters, in this case p, and then there is a body which is represented by an if statement. And then it proceeds further to say, for instance, that the if statement is decomposed by a condition expression and by a call statement. In this case, it's going to be alert. And then further, the condition expression is decomposed into p and true, the two operands. And the call expression is decomposed into, again, the function invocation and the literal that is passed as a parameter. Okay? So at this level of modeling of the code, you can write, well, quite a few interesting rules. For instance, of course, this code that I'm using here now does not come from Prettier. We prepared it on purpose. The rest that you have seen, the initial examples and what you're going to see later is from Prettier. So, what do we have here? Well, here, these are two tokens that look identical. Okay, open curly braces, close curly braces, both here and here. But only in one case, this is an empty block of code. So we can write a rule finding empty blocks of code, but we cannot just stay at the lexical level. We need to be a bit smarter, because this can be an empty block of code, or it could also be as it is in the if condition. So we cannot stay at the lexical level. We need to understand the role of these two curly braces in the context of the if statement. Okay? Then another interesting rule that we can write at this level is, let's imagine that I have these if-else branches, and well, they are fine, they're doing different things, but one day I decide that this part of this logic is not useful anymore. I don't want to execute that operation anymore. And so I delete. And as soon as I have deleted that line, well, at the syntax level, we can notice that, well, these two branches of the if statement, well, they are now equivalent. They are doing exactly the same, and this we can find across an arbitrary large set of branches. So what you do is you just check every branch and you see if all the statements are exactly the same in different branches, and if there are two that are the same, you can point it out. So as I said, at the syntax level you can write a lot of interesting rules. This is just an example. Then next level gets more interesting. This is where we start to move away from what you would expect initially from code modeling. is semantic analysis. Semantic analysis starts with symbols. We try to identify the correlations between different syntax elements and say, yeah, this is one parameter declaration, this is a variable that is being used, but we are able to say, in fact, this is the same variable. It's this parameter that was declared here, and it's used in the if. So we are able to say P is a parameter, and it has one declaration and one read. Okay. Then we can also identify functions and match their declarations down there, and the declaration up there and their usage down there. So there is one declaration, one invocation of this function. Then variable declaration. P is again, P textually looks the same, but in fact it's not the parameter P, it's this variable that is declared here. It's written also here, you see, we say one declaration, one write, and then it's read once when it's passed as a parameter to foo. So at this level of analysis, we can find some other interesting stuff. Classic example of this is, well, really classic in this case. This variable let x is never used, and even if we are declaring something called x here inside this if, we are redeclaring it and it's a let. So in fact we are not using the initial variable that was declared before, we are using a new one and assigning 42, so the first one is still unused. Another classic case, well, we are able to say this x that you are assigning a value to was originally declared as a constant. You see, these two are the same thing, and you can see that this declaration was constant, so you should not be assigning any value. You can just delete it, and that's it. Blink. And there is no problem anymore. And yet another level that you can build on top of this, or besides this, in the same level, it's the control flow graph. Now, the control flow graph is when things start to be a bit less obvious for a human to follow. For instance, take this code, this example code. You can ask yourself, okay, which is, if I invoke this function, if fill array is invoked, what is the first expression that gets evaluated when the program is executed? Well, it might not be obvious for the developer at first sight, but the first thing that happens is that we start by evaluating I smaller than 10. It's the first thing that we do. Then we go further and we keep on running, not really running, but statically analyzing the flow of code that goes to this logic. So the next thing is, well, you evaluate the next side of the condition, which is p strictly equal to true. Then, after that, what happens? You enter the if block. You enter the if block, and then, well, this is a loop. So after you have entered here in the if block, you go back, you increment I++, and then you start over again. So this is the representation of the loop. This is how our loop is behaving in one of its possible branches. But there are other branches. For instance, what happens when p strictly equals to true is false? Well, in that case, we go to else. Else contains a return. So we go to the end. We finish the execution of the function. And there is one extra branch that we must not forget, and that the control flow graph models, is this one. So the shortcut. When I smaller than 10 is false, well, we don't evaluate anything else. We directly go to the else branch and we return. Okay. So once you have built this kind of graph, you can write rules that are more about dead code and stuff that is never reached, etc., etc. It's also important to mention that when we work with the control flow graph, we work with more details than this. This diagram here is simplified. In fact, the control flow graph goes more into the details. For instance, if you look at the array.pushI expression, you will see that, in fact, there is a lot that is happening in there. What is really happening is that the first thing is the interpreter will read the array object and then check that property push exists on the array object, and then read I, and only then execute array.pushI, execute the member call. Okay. So this might sound like a small detail, but in fact it's what allows you to really evaluate one-liners with a lot of logic inside there, just one big expression, and thanks to these details that we have in the CFG, we can really find stuff in complex one-liners. Okay, so what can we do with the CFG? So here, what are we saying? We are saying that this original assignment to x, we say x equals dev number, is useless. Why is it useless? Well, because the only case where x is being read, so the value of x is being read in some way, is here in the console.log. And just before that, what happens? Well, it happens that we are writing some new value to x. So the original value that was assigned to x was useless. This can happen for many different reasons, typically because when you originally wanted to use the initial value for some other case, but then you have not yet written the other case or you've forgotten about it. So for instance, you could do something like using x in another branch, console log. So in this case, in the second branch, you are not reading the new value that was assigned in the true branch. You are reading the original value that was set initially to let x. By navigating the CFG, we are able to see which values are read at which point. Okay? Then, here, pretty straightforward. This is the classic dead code. By navigating the CFG, you can find out that if you look at these if conditions, well, in one case you are returning true, in another case you are throwing an error, and then in the other else you are also throwing something. So there is no way that you ever get to this return false. So this return false is dead code and it's useless and probably misleading. Finally, another example is if you have a switch case with multiple cases. Well, in this case here, you had quite a lot of logic. You thought that you were always returning something from this case, so no need for a break. But in fact, yes, there is the need for a break, because it is possible that you don't enter this block here, nor this block here. So you will get to this line here, and then it will fall through to the next case. So here, you either return something there or you add a break statement. Okay. So this is the CFG. It's not yet evaluating what are the data values, it's just checking all the branches of the code. And to move a step further, I let Elena continue.
Okay, so I'm gonna speak about symbolic execution, or how we call it now, data flow analysis. So we will try to track the data of the program along different paths of execution. So please, can you think of this program in program point? So just after the let statement, before if statement, what is the data of the program which we can certainly know? In fact, we can certainly know just one thing. We know that the message message variable has an undefined value, because as we declare without initialization, it's undefined. So we call it program state. Between each execution step, you have a program state. So what will be the state of the program on the top of which we will apply next step? The next step which will happen, we will check the condition. We will check p equal true or not. So if it is true, we will enter, all condition is true, we will enter the block. We will, the program point will be right here just before assigning the message value, and our program state will contain two pieces of information. Message is still undefined because we still didn't execute the next statement, and p is true because the condition was of this if statement was true as we entered the block. And if we will continue this execution path further, the statement of assignment statement was executed by that moment, so the information about message value has changed. We know that it is print me big literal, and p is still true because nothing happened to p variable. It was not reassigned to something. And then the alert function is called. Everything is fine. And let's now consider another execution path. The one when p equal true, the condition of this if statement is false. That would mean that that block, which is here, is never executed, and we will go directly to the last line. That means that we will keep the message undefined here, and the p is not true, because we know the value of that condition to be evaluated. And now let's look at that statement. What happens here, we will take message and we will call it with, we will access the property to uppercase on it. Does it exist on undefined? For sure not. And we will get a type error here. And thanks to that layer, we can find quite advanced...
Elena, if I may point out, this doesn't mean that we are executing the code for real. It's still static analysis. We are statically finding all of the constraints, so we are not running the code.
Yeah, that's why this is abstract interpretation or something like that, many names for it. So let's see here. We have... this is already fixed.
We already fixed it. Well, let's move to another example.
Okay, and this way. Yeah. So sorry, we fixed that for another demo. So in fact, we were accessing.
In fact, for yesterday.
Yeah, we were accessing the property on form field variable, and as you can see on line 7, its value is assigned either something, which is, we don't know what's that to correct, but in other cases it will be null. So for sure there will be execution path which will lead you to form field being null, which will raise you type error at last line of function. Next case, this is also demo. Sorry. So here it is about base variable. If you look at that condition, we see that it is always true. If we look a bit above, we see that on the first line of function, we check the type of base variable. If it is string, if type of base is string, we will not enter inside of that code block. And the string can never be false, and that condition is true. Another execution path, if base is not string, we will reassign it a new value, and it will be undefined. So again, base, which is undefined, is never false. So we know that this condition is always true.
Let's try it.
Let's try what? Fix the issue.
Yeah.
Yeah, like that. The issue disappears because in the case of base being not string, it could be boolean, it could be false, and this condition might be false as well. This one is a bit tricky to understand, but it's really interesting because it concerns the relations between variables. So we have not only some data, some knowledge about the variable values, but also about their relative, their relationships between each other. So here we base our, the issue is based on the isOpen variable. You see here it is some complex relationships. We reach this line only when isOpen is false. That would mean we will reach it in two cases. Either start is more than today, or today is more than end. Also, we will reach that line only if this one is false. And if this one is false, the first case disappears, and we know that the second one is the only possible option. So there is no point of checking that condition, and there is even else clause. So that means that this else clause doesn't mean any sense. So we should even have some highlighting for that. Yeah, so we would highlight the main issue, the location, and some code which is due to that problem is never executed.
This is real code, but it does not come from Prettier.
Yeah, that's true. And the last issue is variables, but it shows you the relationship on different paths of execution. So here we have a failure message, condition with failure message variable, which is always false. And if we look closer, we see there is a match variable. And if a match is false, we will assign it a value which is opposite to failure message. If it is true, we do nothing. And if it is true, we either don't enter this code block because we match that. That means that when we will enter that body of the if statement, is a match value is always opposite to failure message. And as is a match is false, failure message is true, not failure message is false. So this code block is also never executed. What we can do more on top of that? What we can do more is cross-procedure analysis. So let's imagine exactly the same case which we were doing in the previous slide, but the call to alert message to uppercase, we wrap it inside of another function. Then, if we will remember what we were doing in previous slides, so the same story, message is undefined here, then we go at this line with message being undefined, so that's the unhappy path where we have type error, and p is not equal true. And from perspective of this particular line, there is nothing critical to happen, because you just call function with undefined argument. Nobody cares, nothing wrong about that. But you can do more. You can look inside of that function and see what happens inside it. And if you see inside it, so you will have you inherit the knowledge of variables from calling function to parameter values of the function to be called. So we know that text is and has a value of undefined, and then we will have type error. That's probably our main target in current development. So we are trying to reach this level of execution. And okay, we found an issue.
Yeah, there is another interesting point when you are developing a code analyzer is that, okay, you have built all of these nice models and then you have finally found all of these cool issues. But the work is not over, because there are a few things that you need to make sure of before you really finalize your rules that will find the issues. The first, and I would say the most important from the perception of a user, is that if we raise an issue, we raise it for good reason, and we don't do what we call a false positive. A false positive for us is when you raise an issue, you say to someone that something is wrong, but in fact it's not wrong. That's typically very bad. And it's really difficult to solve all of these false positives. For instance, I will take a very non-controversial rule, which says, hey, if you have commented out code, it's probably not a good thing. If you are commenting out whole blocks of code, you probably should be deleting that code, and anyway you have versions control system, so what are you keeping that in the code for? And it's pretty straightforward. So how will that implementation be? Well, you take the block of code, you try to parse the text inside the block of code, and if it parses using the JavaScript parser, then it means that that comment contains JavaScript code. So you can raise the issue. Straightforward, right? But no, because, well, very often this happens. This is what I call the commented code comments. So you say you add a comment to your code that is commented out. Hey, don't forget to uncomment this line someday. So this piece of text makes the whole bunch of code not parsable JavaScript anymore. So what do? You don't raise an issue anymore. The rest of the code is clearly commented out code. In fact, it's just that part makes it non-valid. So what do? Well, you start trying to parse smaller chunks of it and raise an issue if a part of the comment is JavaScript code. But then what will happen? Well, things happen. Like when the documentation is meant to contain code. When someone introduced a piece of valid JavaScript code in the middle of a comment, because that's the point. And you can guess, for instance, that in Prettier this happens because it's a library that is doing stuff about code. So it's normal that they have some JavaScript code trailing in their comments. So at the end of the day, for some rules, you always end up having some corner cases where you're gonna raise false positives, and it's a game that never brings you down to 0, 0, 0, but the goal is to get as close to 0 as possible, so that when you raise an issue, it's really an issue, and you reduce the noise that you are putting in front of the eyes of the developers as much as you can. Then you have let's say the problem, you have to take care of correctly pointing out secondary locations. Secondary locations are what happens when you are raising some problem that is originating from somewhere else. In the case, it's what Elena shown before. this is in the slide, it's a similar situation, just a different function call in the same code base. So maybe it's a few months older, it's from a previous version of Prettier. You have 4 arguments being passed to a function that was declared with 3. In this case, parent is being passed in a function call, and the function does not have the parent argument. So if you're not pointing the user to the original declaration, well, you can easily see that this was called at line 900 and something, and the function was declared at line 824. And you can well imagine that stuff can be very, very, very far away in big JavaScript files. So from the usability perspective, it's very important. You have also seen the secondary locations about the dead code. It's not enough to just say this condition is always true, and so the else branch of this if statement is always false. If the if is very complex, you really want to highlight the dead code. So that's a secondary location that you need to keep while you're analyzing the code. Along with your discovery of something that is always true, you keep the dead code locations that you have found while doing the analysis. Then there is another evolution of this, a further evolution of this. And you can see it, well, here it's an example, but you have seen it in the last example, that one of the last few examples that we had. You see, when Elena was really explaining to you why this was always true. It took a few minutes to explain exactly how that happened. And you have to, in fact, probably review that explanation multiple times, because it's really not very simple to follow. What we will need is to make that live explanation that Elena just gave, to make it part of what the IDE can explain to you. So going here and say, hey, you see, is open. If it's true, then you enter here. But if it's false, you enter here. And it means that today has to be smaller than and, etc., etc. And look into here as well. How did we get to a certain discovery? What was the process? And this we call flows. So explaining how the data flowed and which was the specific scenario that makes us raise an issue saying this is always true, this is always false, this is always undefined, or this was undefined at least in one branch, etc., etc. On this, we are going to work on it. It's something that you start to really need when your rules go beyond the immediate understandability for a human. You need to start being more explicit, otherwise people will just think that you are wrong, or simply not understand how to fix the issue that you are raising, because they have no clue how that issue appeared in the first place. Okay? And then, again, it's not over. Let's take again this case. You were passing a parameter to a function that only declared 3, and you were passing 4. For you, is this a bug or a code smell? Well, it's not a bug as in it's breaking something, but does the fact that you are passing the parent mean that you were expecting some extra behavior that you are certainly not going to get because the parent argument is not going to be used ever? So is this a bug because the code is going to do something that you did not expect? Or this is just a code smell because there is no real problem? It's just a smelly situation where it might be even something that you do on purpose because you expect to evolve the function in the future. We cannot really know for sure. So the debate between when this is a bug, when this is categorized as a code smell, is endless, and we spend quite some time trying to refine it as much as possible. And it's not, most of the time it's not even about code. Once you have your rule well shaped, the question is still open. Is it bug or code smell? And in the end, this is not enough if you have a project that runs for a long time. If you want to have an overall overview of the quality of your project, how it has evolved, how does it sum up into big numbers. So it's always useful to calculate metrics, to have a history of what has happened, to evaluate the overall technical depth of your project. For most of these things, the analyzer that we develop does all of these calculations, but then it's not stuff that you can show inside an IDE while the developer is coding. So for this, we typically upload this information to another platform. In our case, it's SonarCube. So all of our analysis go to SonarCube server that you can install on your systems, or you can use Sonar Cloud, which is available in the cloud. And what it gives you is an overview of all of your projects with an history. And for this, I'm showing you what we call Next. So next.sonarcube.com is open. You can visit it anytime. And it's the SonarCube instance that we use to store all of the analysis of our own analyzers. So in here, let me search by project, you will find also our own analyzers. So SonarJS, which we have been using for this presentation so far, is being analyzed, and the results are uploaded to our own SonarCube instance. And this is what we see about our analyzers. What we see is that in the last period, we have introduced 2 bugs internally to release. And not only our code coverage is lower than what we would like, which should be like 90%, our target is 90%. So what we show you is that overall, we have 95.2% of code coverage, but in the last period, the code coverage is lowered. So we want to increase it before we release in order to guarantee that our overall quality stays good for the long term. This concept for us is very important because it helps projects with a low quality ranking to progressively increase their quality without any big initiatives, transforming, refactoring everything, etc. You can just focus on small periodical increments that will ensure that your overall tendency is good, even if you are starting from a bad situation. You also can see the technical depth that we calculated during the analysis, etc., etc. And here you can also see the issues in a web form, but this is less interesting because it's the equivalent of what you just saw in the IDE. Okay, so how does this work? How such a layout with an analyzer and history and metrics platform work? So, right. I will take just an example. I will take an example where your project is sitting on GitHub mostly, and you are developing on it. So you install our analyzers plugin, so SonarLint, which is running SonarJS, the SonarJS analyzer inside, and SonarLint is what we've been using for this demonstration. You can, maybe they can hear you, but yes, it works on, here I was using IntelliJ IDEA, but it works on all of the JetBrains branches of IntelliJ IDEA, so WebStorm and company, Visual Studio Code, Visual Studio, Eclipse, for those who care. And it's self-contained into your machine, but what if you are collaborating with multiple people? Well, you want to show your overall metrics and your code quality to everyone. So what you do, that you do a small configuration file, which is Sonar project properties. You give a name to the project key and you push to GitHub. Then in your continuous integration, you use an add-on that is in fact running the same analysis using, again, SonarJS, just not in your IDE, but in the continuous integration environment. And it's running whatever analyzers are required for your code, and it's pushing the results to your desired SonarCube instance. In this case, for instance, it can be pushing it to Sonar Cloud. And then another important thing that you can and should do is you always need to make sure that whatever analysis is happening in Travis is using the same parameters, the same rules that you have in your IDE, because you don't want your IDE to be decorrelated to the overall quality reports that you are publishing. So you should and you can connect your plugin in your IDE to the reference reporting instance for your project. In this case, you should connect to the Sonar Cloud instance. In this way, your plugin will maintain the same rules and the same behavior and same parameterization that you have set up for everybody else in the project. And I can even show you how this will work live. It will take maybe some time. So this is the our fork of the Prettier project, and well, I will take click. Let's take the comment.js, and of course, like everybody does, I will directly edit it in GitHub. I mean, we're all about quality here, so let's do something of high quality. And let's introduce a variable that you remember the first case. This is an octal. So if our rule that is catching octals is enabled, when I'm now committing this change in master, because I mean code quality and best DevOps practices first. We have now updated the code. What is happening in Prettier? Well, in Prettier, in Travis, the build has started, stuff is happening, and at some point it will execute the analysis using our analyzer, our JavaScript analyzer, blah, 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 etc., etc. In the meanwhile, while we wait for Travis to do its stuff, let me go a bit more into the details of the configuration, but just very quickly. Prettier. If the internet helps. Not helping. Okay, Prettier. Gonna make it. So you will find here the setup. It is defining the name of the project in your target SonarCube instance. So the project on SonarCube instance is going to be called Prettier Demo. You have the version, you have the name of the organization, because this is Sonar Cloud, so we support multiple organizations, etc., etc. And then you have your Travis build file. Again, if the internet helps, Travis YAML. And I mean, it looks like the stuff in the slide, nothing super special. And in the meanwhile, whoa, Travis is green, it has finished its build. So what has happened in here? Well, here is where we're pushing our project, right? This is Sonar Cloud, this is the Prettier demo project inside Elena's organization. So let's look at the issues. And lo and behold, we have the internet really slow. We have the issue Travis ran. So it's automatically associated to the person that did the commit, and you can also say something about this. So are you gonna fix it? Are you gonna consider it a false positive? Is it right or wrong what we have raised to you? And you can specify it here. And if you have connected your IDE to SonarCube, well, and you have marked it as a false positive or as fixed, well, we will not show you it in the IDE. So this way it is not going to pollute every other developer IDE if it's something that you really want to have as code. Okay, so that's it. I presume it was not as fluid as it could have been live, but this is the best next thing, and I hope you will like it. Thank you.
Thank you.